Good day, everyone. Welcome to the first module of our Fundamentals of Electric Circuits 1. Okay, so for this module, we will talk about the basic concepts. For the introduction, we have knowledge in basic concepts is essential in studying electric circuits theory. Basic concepts include the theory and computations of the basic or fundamental quantity in an electric circuit like charge, current, and voltage. At the conclusion of this learning module, the learners are expected to number 1, discuss and determine charge and electrons. Number 2, define and determine current. Number 3, define and determine voltage. Number 4, differentiate DC from AC. And lastly, explain sign convention. So hopefully after this module, we will achieve all of these learning outcomes. So let's start. Charge or electric charge is the most basic quantity in an electric circuit. It is also the fundamental property of matter that exhibit electrostatic attraction or repulsion. It is the electrical property of the atomic particles of which matters consist. So the SI unit of electric charge is called coulomb. Okay, so 1 coulomb is equals to 6.242 times 10 raised to 18 electrons. Okay, so that's how many electrons it takes to for us to have 1 coulomb. So that much times 10 raised to 18. Okay, this one here is the equivalent, which is, let's try to show again, 1 coulomb. 1 coulomb is equal to 6.242 times 10 raised to 18 electrons. Okay, that's how many electrons it takes to have 1 coulomb. So for the charge of 1 electron, so we will transpose. We have 1 over 6.242 times 10 raised to 18. Okay, coulombs. Okay. Then, so 1 electron has, we will divide this one, it will be equal to 1.602 times 10 raised to negative 19 coulombs. So this is how much charge 1 electron has, and this is how many electrons 1 coulomb has. Okay, so that's the relationship. The charge of a proton, notice the difference. The charge of a proton is 1.602 times 10 raised to negative 19, and the charge of an electron is negative of that, because as we've learned from our chemistry that proton is positive and electron is negatively charged. Okay, they have the same magnitude, only the sign is different. So a unique feature of electric charge or electricity is the fact that it is mobile. The law of conversion of charge states that charge can neither be created nor destroyed, but only transferred. Thus, the algebraic sum of the electric charges in a system does not change. It can be converted to another form of energy. Okay, so that's it for charge. Next, we have current. Current here is the motion of charge through a conducting material or the time rate of charge. The current is measured in ampere ampere, or the current is symboled as uses the symbol I, capital letter I, and the ampere uses the symbol capital letter A. So ampere is the quantity of total charge that passes through an arbitrary cross section of conducting materials per unit second. Okay. So this is a formula for current in terms of charge. So before we proceed to that, I would just like to give you a better view on how current works. For example, we have this conducting material. In our household, usually we see this conducting material in the form of wires. Okay? And the most common material used for wires is what? Is copper. Okay, so we have copper as the most common conducting wire for electrical purposes. Okay, for example, these are our charges. So this is one, let's say one electron. Okay, so this is one electron, 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 electron. Or let's just say charges. Because it will be a lot of electrons. There will be very, very many electrons that will pass through to our conductor. So if these electrons passes through our conductor, so this one, okay, and let's say the time for this is around 1 second, or let's just say it's time t. Let's just say it's time t. So we have here the amount of charge, then it takes them to cross from point A to point B. I think I'll have a better illustration for this. Okay. So the time it takes for the charges to cross from point A to point B is t, or t time. Then this is the amount of charge that will pass through. So this rate is what we call the current, and this current is equal to charge over time, or Q over T. Okay, so this is what that formula is all about. So I again is the current measured in amperes, Q is the charge measured in coulomb, and T is the time measured in seconds. A direct current is a current that remains constant and does not change with time, while an alternating current is a current that varies sinusoidally and does change with time. Okay. So we have here, in this figure, shows a constant current, or DC current, which is denoted by the symbol I. Okay, so this is the current, this is time. So for a direct current source, or for any source that can produce direct current, so when we try to monitor or graph or trace, measure that current from the direct current source, what we will see is a straight line, meaning whatever the value of the current for that or from that source will be a straight line from all throughout. Usually, this type of current is taken from DC sources. Most common example of DC source is battery. Okay, so for now, almost, if not all, most of our gadgets are mobile, meaning all of them will have batteries. So batteries are producing batteries are DC sources. So the current that they produce is a DC current. It is always a straight line. Next, we have the AC, or alternating current. Okay, so this is a sinusoidally time varying current. Uh, we say sinusoidally because if you are gonna look at the illustration or the graph of the current, it is a sine wave. Sine. Remember from our trigonometry, sine, cosine, whatever. Okay, so it changes bit over time, unlike DC current, which is constant all throughout the operation. So this one, normally, okay, in normal electrical distribution, sine wave, what do you call this one? Sine wave alternates between positive and negative values. Okay, so for examples of sinusoidal source, we have our um, household power source. Okay, for example, that is actually a very good example. What is the value of the household current source in the Philippines? We have 220 volts. Other countries uses 110 volts, like Japan, for example. They use 110 volts. Uh, it is called AC because the current there, or the voltage, when the voltage is varying, the current is also varying. The voltage from our household power source alternates between positive 220 volts and negative 220 volts. Okay, so positive 220, negative 220, positive, and so on and so forth. Each between DC and AC, each of them has their own pros and cons. So it will be discussed maybe in other topics. But if I were to give you an overview, AC is being used for distribution. Okay, so from electric companies to the household, the current is in AC because AC current has less losses compared to DC current. DC current is prone to convert to heat energy when they pass through conducting materials. So that heat is actually a loss. That is electrical energy converted into heat energy. But for AC sources or AC current, or for alternating current, uh, minimal heat, the heating is minimal, so the losses is also minimal as compared to the DC source. So if we're an example, how much charge is represented by 5,200 electrons? If we have 5,200 electrons, how many charge do we have? Okay, so this is our given 5,200 electrons, and remember the always remember this constant, the charge of one electron, that is 1.602 times 10 raised to negative 19 coulombs, and then that is negative if electron, positive if proton. So for the charge, like, we will divide or we will multiply 5,200 by negative 1.602 times 10 raised to negative 19. Okay, so the charge of 5,200 electrons is equals to negative 8.3304 times 10 raised to negative 16 coulombs. Okay, we have our next example. Calculate the amount of charge represented by 5 million protons. Typographical error, which should be 5 million. Okay, again, the charge between protons and electrons is the same, but the protons is positive, the electron is negative. Okay, so we have 5 million protons here, then positive 1.602 times 10 raised to negative 19. So the charge of 5 million protons is equals to 8.01 times 10 raised to negative 13 coulombs. Next example. Determine the current in a circuit if a charge of 100 coulombs passes a given point in 20 seconds. Okay, so we are given charge which is 100 coulombs and time which is 20 seconds, and we are being asked to find for the current. Remember our formula, that is I is equals to Q over T, or current is equals to charge over time, so 100 coulombs over 20 seconds is equals to 5 amperes. Next, remember, the current is always measured through or in series of a circuit element. Okay. This will be, this one. This will be reiterated more in our laboratory activities. So don't worry about that for now. Next, we have the voltage. Voltage is the required energy to move a unit charge through an element. So the voltage is measured in volts. That's the unit, capital V. It is also known as potential difference or electromotive force, or EMF. That is the other name for voltage. So the formula for voltage here is equals to V is equals to W over Q, where V is the voltage measured in volts, W is work or energy measured in joules, and Q is the charge measured in coulombs. Wait, I'll just try to take a peek of what's next. Okay. So I'll give you later the summary between current voltage and the next topic. So you can, hopefully you'll understand better if I give you the summary. Anyway, so we have sample problems here. Determine the voltage in a circuit if a work of 100 joules move a charge of 20 coulombs. Okay, so we have our formula. V is equals to W over Q, given W, or work, which is 100 joules, and our charge 20 coulombs. So 100 joules over 20 coulombs is equals to 5 volts. For the next example, determine the charge in a circuit if there is 20 volts measured in a circuit with an energy of 220 joules. Okay, so you have 20 volts, 220 joules, find the charge. So from our formula, we do a little bit of transposition. So Q is equals to W over V. W is 220 joules over 20 volts, so the charge is 11 coulombs. Remember, the voltage is always measured across or in parallel of an circuit element. So again, we will reiterate this more in the laboratory, or maybe let's try to reiterate it later on the summary. Circuit loads. A load generally refers to a component or a piece of equipment connected to the output of an electric circuit. The load is represented by any one or a combination of the following circuit elements. Another term for circuit load is sink, since it dissipates energy, and the voltage or current supply is also known as source. So from the source to the sink. A good example there will be from our faucet, source of water, going down to the sink, which will receive the water. A load can either be resistive, inductive, or capacitive in nature, or the blend of them. For example, a light bulb is a purely resistive load, whereas a transformer is both inductive and resistive. So these are the symbols of our common loads. We have resistor R, inductor L, and capacitor C. Okay. Let's see what's next. So let's have a little bit of. Okay. So to help us understand better the relationship between the load, uh, the current, and then the voltage. Okay, so let's go back a little bit to the definition of each of them. We have current, which is in amperes. That is the rate of charge flowing through the circuit. The volts or the voltage is also known as an electromagnetic force. Since it is a force, it is the one giving the pushing or pulling or whatever motion is needed. In the case of electricity, so it is the one pushing the current. And the load, in this case, resistor, which is not yet defined, which will be defined more in the next module. But the resistor is limiting the current. That is the definition of resistor. So as you can see in this illustration, I just want to reiterate that voltage is the one which provides the force, and current is the one that is flowing or being pushed around in the circuit. Okay. Next, so sign convention. The standard convention to determine the direction of the current is the flow of protons. Okay. What does this mean? I'll try to explain. Okay. So, for example, we have a voltage source in here. We have a circuit with a load resistor, for example. Okay, so we have a complete circuit. When we say complete circuit, there should be a path from the positive of the from one terminal of the source to the other terminal of the source. Okay, so in this case, we'll go from here. So this is a voltage source. We have the positive and then we have the negative. We have our load here, which is a resistor. And in our circuit, we have the current flowing. Okay. So this one. So what is a sign convention? Sign convention is the what do you call this one? Sign convention is the, when I say convention, I think the much better term is, I can find a better term. I can think of a better term. A sign. Okay. So sign convention is the assigned label or whatever to our current. Anyway, let's move on from the definition of convention or the other word for convention. But let's go with this. Okay, we have two types of sign convention. We have actual and no. I'm thinking of another topic. Anyway, so in the case of our circuit, for example, so this is the direction of the current. Usually, we call this the conventional flow. When it's conventional flow, the current flows from the positive of the positive of the source to the negative of the source. As you can see here, the current will move. I'll try to trace this one better. So the current will move from the positive of the voltage source going back to the negative of the voltage source. That is the conventional flow. Okay? And when we say sign convention, meaning how do we treat the signs in our components? Okay, as you can see in here, all positive from the positive terminal of the voltage source to go to the first terminal of the load or any component that the current will pass through from the positive of the voltage source will be treated as positive. Then the other terminal where the current will go out is negative. Okay, so the sign convention basically says that the terminal where the current goes in is positive and the terminal where the current goes out is negative. Okay, if we add other components here, for example, we add another resistor in here. Since the current is flowing from this direction, so positive, negative, the current will go in. Okay, so this is positive again. The current will go out, so this is negative. If we add other components, okay. So if we add other components, for example, we add inductor. Let's add an inductor here. This is the symbol of an inductor, the schematic symbol of an inductor. So this side, the current will go in, so this side will be positive. The current will go out, so this side will be negative. Okay, so that is what we call the sign convention. I'll add another thing regarding conventional flow. We have two types of current flows. You have the conventional flow, and then the other one is what we call actual flow. Okay, so conventional flow and actual flow. Conventional flow, or let's just line this one red since we have the red one already in the circuit. Conventional flow is where the current flows from positive to negative, okay, of the voltage source. The actual flow, let's color this, what color can we use? This one. So the actual flow is the opposite, okay. The current here flows from the negative to positive. This is the correct flow as the word actual. This is not correct. But the more commonly used flow when analyzing circuits is the conventional flow. Why is that? Okay. Before the actual flow was before the actual flow was discovered, it was thought that it was protons that is traveling or is moving in electricity. Okay, that's the conventional flow. So from the positive to the negative, so the protons are the one moving around in a circuit. But years after that, it was discovered that it is actually the electrons that is moving around the electric circuit. So meaning, it should be flowing from negative to positive since it is actually the electrons that is moving as we've discussed, charges. Okay? Then why don't they abandon conventional flow and change everything to actual flow? Before the actual flow was discovered, there is a large time difference from the establishment of the actual flow and when conventional flow was established. So the conventional flow was already used for a very long time before actual flow was discovered. If we look at the solution, there is actually no difference when we use actual flow and conventional flow in terms of the numbers. The numbers will be the same, only that the direction of the current will be different. So, since the numbers will be the same, there will actually be no big difference if we will use conventional flow and actual flow. The reason why conventional flow is the more popular and the one that is actually being used is because, again, a large time from the establishment of conventional flow and actual flow. So there are so many. What did they say? So many. There are many educational materials, research papers, studies, journals, newspapers, books, okay, that has already used conventional flow. So, if they are to recall all of those materials and re re-edit everything inside or what is written inside those materials with actual flow, it will take a very long time. It will need a lot of money, a lot of resources. But if you look at it, the result or the magnitude or the numbers will still be the same. So they deemed it unnecessary to replace all of the materials using conventional flow with actual flow. So up until today, we are still using conventional flow when when we do analysis on circuits. Okay, so that's with conventional flow and actual flow. We go with conventional flow. Uh, what else? What else? Regarding the have you did your screenshot already? Regarding the what do you call this one? Ammeter and then the ohmmeter. Ammeter and voltmeter. Measuring current and measuring voltage. This is just an overview. This is not really we will not go really deep into that. But again, recall that the current is flowing around the circuit while the voltage is only present on the components. So if we are to measure current, we use ammeter. Okay, ammeter is the material or is the equipment being used to measure the current. So when we measure current, we connect it in series with the circuit so that the current can pass through the ammeter since it is using or since it is measuring current. Okay. For the case of the voltmeter, which is measuring voltage, the voltage again is only on each components. There is no voltage on the wires or the connections. Okay. So it will be connected in parallel with the material. So, V for voltage. Okay. So same with this resistor. So for parallel and series connection, we will discuss this more. We will discuss more about that in our next modules. Okay, so that's all for today. That's all for now. That's for our first module for fundamentals of electric circuits 1.